When antenna engineers design and simulate an antenna, one of the key parameter or the first parameter that they will be checking is S11 or VSWR. So in these videos, we are going to explore more about what is meant by VSWR, S11 and return loss. To know the importance of these parameters, let's start with maximum power transfer. So maximum power transfer says that if a source is connected to the load for a maximum power transfer to occur, the load impedance should be the complex conjugate of the source impedance. Then only maximum power transfer occurs. That means that both load and source has to be impedance matched. So in our practical case, that is mean by in our antenna cases, these antennas are connected to the cables through the sources. So we have to make sure that the cable impedance is matched to that of antenna impedance. So this is one of the analogy which is used to usually introduce the impedance matching. So here we can take the diameter of this ose as the impedance. So here we can see that this ose has more diameter and this has less diameter. That means the diameter of this ose and this ose are not matched. So here you can see that when the water is flowing from this hose to the another hose, you can see that the water is getting leaked. Similarly, in our case also, if the impedance of the cable is not matched to that of the antenna, some part of the power will be reflected back and only some part will be transmitted through the antenna. In order to check that, that means if our cable is completely matched to the antenna or if it is not matched, how much power is getting reflected back, we need some quantitative parameters. So these VSWR, S11 and return loss serves this purpose. These are closely related parameters. This gives an indication about how much is the reflected power with respect to the incident or this feed power. Let's see what is meant by VSWR. In some industries, it's sometimes called VSWR. Let's consider an antenna is connected to the source through a cable and we are giving some power to the antenna and this is our input power, that is the power which is going through this cable. Here you can see that its value is around 1 volt which is going through this feed and which is going to feed this antenna. Depending upon the impedance matching between this cable and antenna, some part of the power will be reflected back. So let's assume that my antenna is not matched to this feed cable and around 70% of the power is getting reflected back. So here you can see that this blue is the uh, coming from our feed and this orange one is the whatever is getting reflected from the antenna due to the mismatch. Here you can see that the amplitude of this feed power and the reflected power is not varying, but you can see that the phases are varying depending upon the reflection. So this is the source position and this is the antenna position. So here what you have to notice, the magnitude is never changing for the incident and reflected, but you can see that their phase is getting varied. Due to these interactions, standing waves are getting formed. So here you can see that blue is my feed power and orange is the reflected power. Their magnitude is not changed, but because of their phase varying interactions, you can see standing waves are formed. This green line is the standing waves. Here you can see that when both are in opposing direction, that is in a destructive interference, the value of standing wave is getting minimum, and when it is in the same phase, here you can see both are getting in the same phase. You can see the standing wave is getting maximum value. So I have put two screenshot of these animations to see what is meant by V max and V minimum. So here you can see that both incident and the reflected wave is coming in phase, and because of these interactions, the resulting wave will have the maximum power. So this V max is V incident plus V reflected. So this is the second screenshot. Here you can see that the incident and reflected wave is coming in destructive mode, and because of that the standing wave magnitude is getting reduced, because these standing waves are mainly formed because of the interaction between the incident and reflected wave. Here you can see that means when both are in phase they will get added up, when both are in uh, means destructive mode they will get subtracted, and V minimum will be equal to, that is this value will be equal to V incident minus V reflected. So because of the interaction of incident and the reflected field, we are getting the standing waves. So the ratio of this maximum value to this minimum value is known as the voltage standing wave ratio. So I have put all these animation together. Here you can see that the incident wave, and here you can see that the reflected wave. There is no change in the magnitude of this incident and reflected wave, but because of the phase variation, their interaction is producing standing waves. You can see the standing wave magnitude is getting increased and then it is getting decreased based on the value of this incident and reflected wave. And we have seen how the maximum value of the standing wave and the minimum value of the standing wave is getting produced. So the voltage standing wave ratio is defined as the ratio of this maximum value of voltage and the minimum value of voltage. So here I have taken the animation of that standing wave alone to get a better picture about the Vmax and Vminimum. When you observe this peak, you can see that it is getting reduced and it is touching Vminimum and it is again going to Vmaximum. So this ratio is known as the voltage standing wave ratio. So voltage standing wave ratio actually measures the ratio of the maximum voltage inside the cable. What is happening in the cable? Because we can see that when the incident wave is hitting on the antenna, some part is getting reflected back, and these standing waves are happening inside the cable. So VSWR is actually measured in cable, and it is defined as the ratio of maximum to minimum voltage in a transmission line, because we know that the standing waves are actually occurring in the cable. I just want to emphasize that the maximum of this standing wave produced due to the interaction of incident and reflected wave will be the sum of both incident and reflected wave, and the V minimum of the standing wave will be the difference of incident and reflected wave. Let's see the interpretations of VSWR for the ideal case and the worst case. Ideal case means whatever be the power feeding to the antenna, it is completely radiating and there is no reflection. So in that case, you can see that this is the input power or the feed power, and as there is no reflection, there won't be any standing wave, because standing waves are produced due to the interaction of incident and reflected wave. As there is no reflected wave here, no standing waves will be produced, so the reflected wave will be zero. So we know that VSWR is V max by V minimum. So we are actually measuring the voltage maximum and voltage minimum in the cable. So we know that V maximum is V incident plus V reflected, and V minimum is V incident minus V reflected. As the V reflect is equal to 0, this will become 1. Here you can see that this is the maximum and minimum value of the voltage that is occurring inside the cable. So the VSWR become 1. So in the case of no reflection, VSWR is the 1. It is the ideal case. And when complete reflection case, that is the antenna is open or short, we know that the complete reflection will occur. So here you can see that amplitude of the incident and amplitude of the reflected wave is same. So we can say that V reflected equal to V incident. Here you can see the interaction. When both are destructive, the value is 0, and when both are constructive, the value is going maximum. So both destructive, you can see the value is becoming 0. So the VSWR can be written by Vmax by V minimum, as in the case V reflected is equal to V incident. This will become 0 and VSWR become infinity. So these are the key interpretations. So our ideal condition, for the ideal condition, we should have VSWR of 1. But we know that that is not possible because there may be some sort of impedance match between the feed line and the antenna. And means this is the worst case where VSWR is infinity. Let's see what is the accepted limit of VSWR. So in most of the industries accepted, the power reflection level is 10 to 11 percentage. So we know that power is related to square of the voltage. So this will be correlated to voltage reflection of 0.33. You can calculate that by taking the square root of 10, and you will get then voltage reflection allowed is 0.33. So here what I am considering is I am considering 1 volt of power, 1 volt of signal. Here you can see that the blue is the incident signal and its value is 1, and I am considering the reflection of 0.33. Here you can see that the reflection level is 0.33 volt. So VSWR can be calculated by Vmax by V minimum. We know that Vmax is V incident plus V reflected, and V min is V incident minus V reflected. V incident is 1 and V reflected is 0.33. So it can be calculated as 1.33 by 0.67. So it is equal to 2. So we got VSWR as 2 is to 1. This is the accepted level of VSWR. So if our antenna uh, simulation shows a VSWR of 2 or less than 2, we can say that antenna is performing well, or the reflected power from the antenna is less than 10 percentage. So it is working in good condition. So we have to make sure that VSWR is less than 2 in our antenna design conditions. Our next video will be on other parameter return loss. I hope you get some idea about what is meant by VSWR. If you find any of our videos useful, kindly support by liking, commenting, sharing and subscribing. Thank you.